record. There we go. Now we'll go back. Okay, so take two. All right, variations. So when you hear the word variation, I don't want to do that. Come on. You think of change. Things are varying. More specifically, you're examining how two or more variables impact each other. So that's what variation is. How do two or more variables impact each other? So if you change x, how does y change? That's what we're looking at. Or sometimes we have three or more variables. That could happen too. So really a lot of this is going to be about making equations. Because that's what an equation is anyway. It's a relationship between two or more variables. That's what an equation ever is. It's a relationship. And we're going to look at more real life relationships between variables in just a sec. So let's start with direct variation. So what this means is that x and y directly impact each other. That's what that means. And the equation is this: y equals a times x. So for example, if I double x, you double y. If I triple x, triple y. If you quadruple x, you quadruple y. Or if you take half of x, you take half of y. So they have a direct impact on each other. A is called a constant of variation, so just a number. It's just a number. And it helps you to figure out or get a clear picture of this relationship between x and y. So in this case, circumference of a circle varies directly as the diameter of a circle. Hopefully you guys remember circumference. So that's the equation here. So that's the answer for example one. C equals pi times t. It follows, it's similar. Y equals a times x. So the c is like the y, the d is like the x, and your a value is pi. So your constant of variation here is pi. Pi is a number, we know this, 3.14. We're very, very familiar with that. And so that just helps to describe the relationship between circumference and diameter. So for example, if a circle has a diameter of 10, the circumference would be 10 pi. That's just how circles work. So we have an equation to describe that relationship between those two values. Another way you can think of this too, that C over D equals pi. If I divide both sides by the diameter, we get this as well. This tells me that the ratio between circumference and diameter is just pi, which is a constant, because it doesn't change, right? Pi is pi. So that's the other thing about direct variation, is that they're always in a constant ratio. And by the way, because I'm recording this, I would strongly suggest that you rewatch this. I'll post this to Schoology after we're done today. But I would strongly suggest that you rewatch this as a way to help you study for the quiz next week. Because I think hearing this stuff again sometimes helps. So that's also a great way to help you thrive in an online learning environment, is rewatching video lessons can help. Anyway, so that's what to expect for direct variation. Let's look at one more example before we move on to inverse. So again, it's just a constant ratio. So now let's look at example 2. I'm going to go ahead and clear all this because it's getting very messy. All right. So you're driving at 50 miles per hour on a highway. Distance traveled varies directly as the number of hours driving. So distance I'm going to call D. Number of hours I'm going to call T for time. You guys should be familiar with this. Distance equals rate times time. That's a very common formula here. And you already know the rate is 50. The equation is easy. There you go. And that's going to be A. The constant of variation. So your constant of variation is just 50. And your equation is right there. That makes sense because what if you travel for 2 hours? How long have you been on the road? Or sorry, how many miles have you traveled? 100 miles, right? Or what if you travel for 4 hours? You've been on the road for 200 miles, right? So D over T equals 50. That's consistent. So that's a common ratio. So that's what you expect for direct variation. And yeah, that's a real life thing. I mean, a lot of people drive in their car, right? And so, how does distance and time relate to each other in a constant ratio? Let's assume that you keep the same speed. Let's move on to inverse. Now, inverse is the opposite of direct. So in this case, X and Y impact each other in opposite directions. So let me give you a good example before we do example 3. Let's say you're building a house. Let's say you got 8 people. It'll take them 4 months to build a house. What if you decide to bring more people in to help you? If you double the workforce, how many months would it take to finish building the house? Anyone want to chime in?
Half the time.
So 2 months, good. Thank you, Armin. That's inverse variation. So basically, if you double, say you double X, then you take half Y. So you go in opposite directions, so multiplying by 2, what's the inverse of multiplying? Dividing. So instead of multiply by 2, I divide by 2. Or what if I triple X, then divide by 3 for Y? What if I quadruple X, then divide Y by 4? So they go in opposite directions. And the relationship is right here. Y equals A over X. Another way you can think about this too is that X times Y equals A. So we think of this as a constant product now. Direct was constant ratio. Inverse is a constant product. Notice that 8 times 4 is 32. 16 times 2 is 32. So that's what's happening with inverse variation. And these are real life relationships, right? I mean, we see construction. I mean, of course, construction is halted because of it's not considered an essential business. But once things get up and running again, we're going to see a lot more construction, a lot more people going back to work. And so, yeah, I mean, we see that kind of that relationship that if you have more people to do a project, it would take less time to get it done, right? Or if you have fewer people, it would take more time to get it done. So let's look at example 3 here. So family plan offers 20 gigabytes of shared data. So say you're on a cell phone plan with your family. What's the relationship between the number of people on the data plan and the data limit per person? Okay, so let me erase all this right now. Let's change the colors up for a little variety. So this is going to be your constant. That's not going to change. I mean, obviously you can change your plan if you call or go online and change your cell phone data plan, but we'll assume that stays the same. Your parents are not going to change it, right? So the number of people, let's say I call that X, and the data limit per person, let's say I call that Y. So just going to be Y equals 20 over X. There you go. That should make sense because let's make a little table here off to the side. For example, right now my children are 3 years old and 5 months old, right? So actually my dog's almost going to turn 6 months. It's crazy. They don't have cell phones, right? So just me and my wife on the plan. So there's 2 people on our plan. So we each get to use 10 gigabytes. I tend to use more during the sports season because I'm watching a lot of highlights on my phone. But yeah, that's kind of how it is, right? But she takes a lot of pictures and videos, so I don't know. But all balanced. When my kids get older, I don't know, maybe when they're in middle school, they want cell phones. So there's 4 of us now. Now it'll be 5. Notice how by doubling the number of people on the plan, the data limit per person drops, right? So that's why it's an inverse relationship. And if we add more people to the plan, let's say there are 10 people on the plan, then it's only 2 gigabytes per person. So 2 people, 10 gigabytes per person, right? But with 4 people, 5 gigabytes per person. So that's an inverse relationship. That's why I'm going to write my equation like that. Or X times Y equals 20. So it's a constant product. Let's look at example 4 now. It takes me 5 hours to clean my house. If I get my fiance to help me clean it, it takes us, I think Ms. Wong wrote this right when she got engaged. So anyway, because I have a wife now, not a fiance. Anyway, it takes me 5 hours to clean my house. If I get my fiance to help me clean it, it takes half the time. That makes sense. Okay. So let's say X is the number of people. And say total cleaning time is Y. And that kind of makes sense, right? Like if I'm one person, I clean in 5 hours. 2 people, it actually takes 2.5 hours, right? Half the time. So is this direct, inverse, or is it neither? What do you guys think?
Inverse.
Inverse, totally inverse, yeah. And relationship would just be Y equals, we'll say 5 over X, because cleaning the whole house on my own took 5. Obviously, I can just plug this in. If you have Y equals A over X, you can plug in 5 for Y and 1 for X. You get A is 5. So that's why I can say my equation is Y equals 5 over X. And we'll do more practice problems like this in just a little bit. Okay, let's keep moving. Now we're going to determine whether we're doing an inverse, direct, or sometimes you might have neither. Then we're going to do some examples here. And then we're going to talk about one other thing called joint variation. Then you guys are going to break into groups. All right, so remember, Y equals A times X, or if A equals Y over X, That's direct. If y equals a over x, or x times y equals a, that's inverse. If your equation doesn't quite look like that, then you're going to say neither. So I'll tell you right now that two of these equations in number one are going to be direct. Which one do you think will be direct?
Second.
What part? A, B, C, D, or E, or F?
B.
B is not actually.
B is neither, right?
Yeah, actually, let's talk about that first. I'm glad you brought that up.
Because it's an addition sign.
Yeah, let me.
When it go, oh, does it wait? So does that mean that for direct, they have to be the exact same number?
Well, you can't. You have to have it like this. You can't have anything be added or subtracted. Let me explain why.
All right.
B is going to be neither. And by the way, F is going to be neither as well. We might as well talk about that. Here's the reason why. If you make a table for each of these, and just randomly pick values of x, like say x is 1, of course y is 4, x is 2, y is 5, x is 3, y is 6. So what's happening here is that x and y are not constant ratios. If I take the ratio between the first pair, 1 and 4, so if I do like y over x, I get 4, right? If I do the next pair, I get 5 over 2.
Yeah.
If I do the next pair, I get 6 over 3. None of those ratios are the same. That's why it doesn't follow. It's that plus 3 messes us up. So you can't have that. You need to have quickly. So what this means is that D is definitely going to be direct. And E is also going to be direct because you can say y equals 5 times x. So whenever it's set up in this way that you see in blue, that's going to be direct. Going back to neither, so for F, if I plug in 1 for x, I get 1, of course. If I plug in 2 for x, I get 4. Plug in 3 for x, I get 9. Plug in 4 for x, I get 16. So there's a relationship. It's a nice pattern, actually, that y is always being the square of x. Of course, you're squaring x, right? But if you look at the ratios, 1 over 1, 4 over 2, 9 over 3, 16 over 4, they're never the same ratio. So that's why it's neither. You can't have the square symbol. So a direct variation, by the way, if you were to graph it, like if you were to graph D or E, it's just a line with y-intercept of 0. That's what we expect. Inverse, however, needs to be in a constant product. Like if you look at B and F again, let me wipe this out here. Yeah, if you look at like F, for example, if I were to multiply all the pairs, 1 and 1, 2 and 4, 3 and 9, that's not a constant product. All those products are different. Likewise for B, I did 1 times 4, 2 times 5, 3 times 6. That's not a constant product, so forget about it. However, A and F are inverses because they follow that constant product, or the relationship that we see with y equals a over x. And if you were to actually make a table, like for C, for example, if I were to make a table, plug in 1, I get 4, plug in 2, I get 2, plug in 4, I get 1. All those pairs are going to be a constant product. Every pair is multiplying to 4. So that tells us we have an inverse relationship. Whereas for D and E, every ratio was consistent. So hopefully that makes sense of understanding how to distinguish among direct, inverse, and neither.
Yeah.
Now for 2, you're told that you have inverse. So let me clear this so it's not distracting. Let me scroll. Okay. So we'll go black in this case. So you're told you're doing inverse, right? So in this case, y equals a over x. That's the formula you have. And you don't have to worry about memorizing it because, you have your notes. You'll have your notes for both quizzes and tests for the rest of the year. So, but once you get the hang of it, you really kind of just know it. You won't forget. So obviously you're told y and x equal. So a is going to be 28. So your equation is y equals 28 over x. Boom. There you go. And the constant of variation, of course, is 28, because that's what a was, right? And now you have an equation. Now we can actually predict. That's the beauty about understanding relationships among variables. Once you understand the relationship, you can use it as a predictive model. Of course, this is a very simple model. It's a very simple equation. But like when people are trying to predict, like, hey, how many more people are going to get coronavirus, you have these, very sophisticated statisticians who are looking at patterns, right? They're looking at social norms. Of course, human behavior is very, very unpredictable. But they're looking at like, how many people are going to the hospital, historical data, treatments. Maybe they're looking at patients' characteristics. So, a lot of that stuff that you start hearing in the news about, like predicting how many people are going to get sick, or even the stock market, like predicting what's going to happen to the stock market. That stock market's been wild. But they're looking at a lot of historical trends, maybe when the market was really bad 12 years ago, or the Great Depression, or right after 9/11. A lot of that's math, very sophisticated and complex math, mind you. But that's the beauty about once you have an equation, you can use it to predict things. So C, of course, I'm predicting what y equals when x equals -2, because now I have a relationship. Sorry, I'm kind of my soapbox there for a little bit, promoting why math's important. But yeah, you always want to think of equations as relationships. It's really a mindset more than anything else. Once you kind of think of it that way, this stuff doesn't really seem to be all that bad. Let's look at 3 next. Now you're told these are varying directly. So P equals A times K. That's relationship now. And we've already investigated relationships, so we feel comfortable that would be a direct relationship. You're given some data points to use. P is 12, K is 4. So of course, A is 3. So your equation is P equals 3K. So again, you're told how P and K are related. You're given some data that you can plug in, and you make your equation. The constant of variation, of course, is 3. And you can use this to predict what P equals. 3 times -2, so P is going to be -6. So, yeah, again, pretty straightforward there. Any questions so far? Nope. Okay. You've actually, if you're a sophomore, or a junior, you've probably already seen this. In chemistry, there are a lot of formulas that actually follow these kind of relationships, especially when you're dealing with gases. All the gas laws follow this kind of stuff. So there's one gas law called Boyle's law. It states that the pressure of a gas varies inversely with volume. So pressure equals A over V. Or actually, they asked you to use K for the constant variation, so fine. I'll use K instead. The letter you use for the constant doesn't really matter. It's kind of up to you, whatever letter you want. But remember, a constant is a number, though. I know it's weird because you see a letter, but it is something that won't change. I know that that term was used often for those who took the PST last fall. They say something is a constant. It's just a number. That's all it is. Just a number. But sometimes we use a letter because we don't have any other data points to plug in for the things that do change. pressure and volume will change. But for numbers 2 and 3 that we just did, we have some data points we can use for obvious reasons. And so then I was able to figure out the constant, how X and Y were, or the variables were related. Okay, we're ready to do some practice problems. Let's look at one other concept, and then I'll break you guys into groups. Joint variation. Joint variation is when you're dealing with 3 or more variables. So you can see how you have Z, X, and Y. And what it is it's when a quantity varies directly with 2 or more other quantities. So you're gonna have one quantity on the left side, like in this case, you got Z on the left side, and you have 2 other variables on the other side, X and Y. And your constant's still A. We're still using A as a constant. Or here's yet another example, P equals A times Q times R times S. So now you're dealing with 4 variables, P, Q, R, and S. So jointly, if you think about joint means together. Like for example, if you have a joint account with your parents, that means that you and your parents are on the account, right? Or you're joining 2 things, right? So that's one way to think about it. So here, just asked to write equations for the given relation. So inverse, jointly, inverse, directly, and inverse, and then jointly and inverse. So we have all these different relationships going on here. So this one is going to be y equals a over x, because that's it, right? For b, w varies jointly with x, y, and z. There you go. W equals a, x, y, z. For c, y varies inversely, but with the square of x. So it's going to be a over x squared. That will actually be kind of important when you move on to physics. I believe many of you guys will probably be taking physics next year. There are a lot of physics formulas that follow this. They say, oh, yeah, something varies inversely with a square. So you do have to pay attention to other words in the statement, not just whether you're doing directly or inversely or jointly, but is the variable being changed in some other manner? In this case, x is being squared. So you do have to be careful about that. Here, z varies directly with y, but inversely with x. So you got that right there as well. So that's also what's going on. Here, x varies jointly with t. So you're going to say a times t times r, but inverse with s, so s goes on the bottom. So remember, with inverse, you're putting on the bottom. When it's direct, you're putting it up top. Because obviously, if you're direct, you want both variables to directly impact each other. If it's inverse, you want opposite directions. So hopefully that makes some sense there, and you guys are comfortable with what's going on. Any questions? Nope. Okay. So we'll go ahead and clear all this. Let's do this. Let's go to the classwork, which you guys should have. And if you could just click on problem sets, you'll find a school G. Let me minimize this. Excuse me. So you guys have been working on 8.1. I'm just ask you guys to do number 1, you have inverse here. Number 3, you have jointly. And number 5, which is a word problem, and you have the word directly. So you guys can do 1, 3, 5. So now I'm going to put you guys in breakout rooms. We'll do 4 breakout rooms, done randomly. And I will set this for 6 minutes. So you guys should, so again, it's 135 from the 8.1 classwork. And open up the rooms, and you guys will go. And I'll just peek my head in every minute or so to make sure you guys are doing okay. All right. Just waiting for some more people to come back. Okay, looks like everyone is back. Perfect. Okay, great. So let's just quickly go over the answers. Then we're going to talk about 8.2. So for 8.1, let me expand this. So the answer keys, all the answer keys, everything that you need is in Schoology. So for number 1, you're told, oh, let me share my screen. Sorry about that. Here we go. Perfect. Yeah. So for number 1, you're told that you vary inversely between x and y. So doing y equals k over x. I did k back in the day. Yeah, you can use a. It doesn't really matter. We'll just use a for consistency purposes. So yeah, y equals a over x. Plug in the data you know, -4 for y, 5 for x, solve for a, you get -20. So that's your equation. And then plug in 3 to predict what y equals to get -20 over 3. Very easy. For 3, you're told we're varying jointly. Again, you can use a for your constant. I used k back in the day. Doesn't really matter. Z equals a times x times y. Plug in the data you have, 24 for z, 2 for x, -6 for y. Solve for a, get -2. Boom, you got your equation. And then, yeah, then you're just predicting. Plug -4 for x, 5 for y, work it out. There we go. Very easy. For 5, you're told there's a direct variation. They use the word direct proportional, same thing. So y equals a times x. You solve for a is going to be 20 over 6, reduces to 10/3. There's your equation. Then you're going to plug in 9 for x to predict what y equals, and you get 30. That's why it's e. Or if you so desire, you could have done this. 20 over 6, because that's y over x, right? Equals y over 9. 180 equals 6y. Y is 30. That could have been fine also if you wanted to approach it that way. Same thing, you know? So any questions about 1, 3, 5 here? No? Okay. I will suggest you guys do 2, 4, 6 over the weekend to get some extra practice with this. And there's actually plenty of practice in the lecture notes as well. Because we haven't really done these practice questions yet on page 3 and page 4. So I'll suggest that as well. And the answers are all in Schoology. So you guys have plenty of practice over the weekend to prepare for the quiz next week. Okay, we're going to keep moving. Let's look at we'll go back to the lecture notes, and let's look at, I think we may have done these already, I don't remember. If we have, that's fine. But let's talk about how to graph one of these equations from 8.2. And then I'm going to have you guys try one, or maybe try a couple, actually, in the problem sets. So I'll do examples maybe one in, I'll do 1 and 2 here. So kind of recap from before spring break, you may have forgotten. There is a general formula that goes with these equations, which looks like that. As you probably can guess, H is going to be the horizontal shift. And K is going to be the vertical shift, just like we've always had. Before I do the actual equation for example 1 here, let's talk about the parent graph. The parent graph is this. We call this a simple rational equation. A is just 1, H is just 0, and K is just 0. So it's very, very, very basic. And of course, this is an inverse relationship. Between X and Y. So it's somewhat tied to what we just did in the previous section. If I were to fill out the table, it should be real easy. -1/5, -1/2, -1. Undefined, by the way, you can't divide by 0. So UND's abbreviated for undefined. Then 1, 1/2, and 1/5. So if I were to actually plot those points over here, -1, -1, -2, -1/2, some kind of like that there. Then 1, 1, 2, 1/2, 5, 1/5. And it's undefined at x equals 0. What that's going to imply is a vertical asymptote. So you are going to have a vertical asymptote at x equals 0. And actually, we're going to have a horizontal asymptote as well at y equals 0. I'll explain all that stuff in just a little bit. The graph will kind of look like this. That's generally how these graphs look when there's an inverse relationship between x and y, which kind of makes sense because as x gets bigger, as x increases, y should decrease, right? Or if x decreases, the y should increase. Again, that's what we kind of expect. But really also what's happening with the asymptotes, as x approaches positive or negative infinity, y approaches 0. That explains all that we're seeing there. As x gets really large or really negative, y gets closer and closer to 0, which kind of makes sense because you're doing 1 over x. So 1 over a big number is essentially 0 or close to 0. The vertical asymptote, as x gets closer to 0, y is approaching positive or negative infinity. So if I do like 1 over a small number, like that, that's going to be 1,000 if you work on the calculator. So as x gets really tiny, really close to 0, we notice that y kind of goes haywire, right? It starts shooting up or shooting down. That explains the asymptotes. But you could think of it, if you want to generalize it, h is kind of like the vertical asymptote, and k is like the horizontal asymptote. If you do want to generalize it, you can, because that's what we're going to do for the actual equation here for number 1. So let's actually look at that now. Let me change colors up. So when we compare the equation number 1 to the general form, y equals a over x minus h, then plus k off to the side, what are our a, h, and k values for this equation here? Anyone can chime in. Well, what's a?
5.
What's h?
-1, and k is -2.
Good, thank you. Let me clean up just a little bit. So let me clear this graph because I need space, obviously. So let's see here. Okay. So yeah, that's my h and k value. So what I could do is I could draw an asymptote at -1. Because I can't plug in -1 anyway. I'm going to draw another asymptote at -2 for y. The main reason why I'm doing that is that this fraction gets close to 0 when x is super big. If x is super, super big, like say 1,000,000, you're getting 5 over 1,000,001, which is a really, really tiny number, -2. That's really close to -2 then, because the fraction gets close to 0 and they have a -2 off to the side. So that's a way to think about the horizontal asymptotes. Is that what is y approaching as x gets really large? So k is always going to be our horizontal asymptote, which is -2. H is going to be our vertical asymptote, which is -1. I know it sounds a little counterintuitive because H is a horizontal shift and it's a vertical asymptote. But if you're moving left and right, you're moving the vertical asymptote that way. And if you're moving, up and down with K, that's actually moving the horizontal asymptote. Then what I would do for your table here, choose x values. Let me write that more neatly. Choose x values above h and below h. So I'm going to do like 0 and 1, and -2 and -3. Essentially, I'm choosing values to the left of the vertical asymptotes and to the right of the vertical asymptotes. So choose values above h and below h. If I were to do that, if I plug in 0 into this equation here, I should get 5 minus 2 or 3. If I plug 1 in, I will get 5 over 2 minus 2, which I think is 0.5. So I'll plot those points. if I plug in -2, I get -5 minus 2, or -7. If I plug in -3, I get 5 over -2, which is -2.5 minus 2, or -4.5. Because you have asymptotes, I mean, that's kind of the whole point. You kind of want to go against asymptotes. Why have them in the first place? Excuse me. And that's how you make the graph. So that's how you would graph one of these here. Any questions so far? How I generate that graph? I want to do one more with you guys before you guys do some practice. Okay, so let me go ahead and clear this. We'll do this one kind of quickly here. H is -2, K is 3. So you do this. Choose values above H and below H. Throw them into the equation. That'll be -5 plus 3, which is -2. Plug in 0. That'll be 0.5, I think. So you have this branch. Plug in -3. You get 8. Plug in -4, -5 or -2 is 2.5 plus 3, 5.5. So there you go. Domain range, I forgot to talk about that. You can see all real except -2, and all real except 3. So you're always going to put H here and K there, because obviously you can't plug in -2 for X, right? That's obvious. The 3, because that's part of the horizontal asymptote, we're getting really close to 3, but never exactly 3. So that's why it's excluded from the range. Plus the graph, you kind of see it, right? All y values are covered except 3. That's how those problems are done. Okay, so remember, just try to identify H and K first, then pick some X values above H and below H, plot the points, and then you have your graph. So it's a pretty straightforward process if you don't overthink it. So I'm going to clear this, and I'm going to show you guys what I want you to do. I want you guys to go to 8.2. I think we did some of these prior, one of the other, maybe 2 weeks ago. I want you guys to do 4 and 5 here. On the 8.2 classwork, obviously here H is 1 and K is 0. Right? Here H is 0. K is -7. Don't worry about the A part. The A kind of takes care of itself when you make the table. Then you'll make a little, table. And you're going to pick H values above and below, or say X values above and below H to get your points. So you guys in breakout rooms again. And we'll spend, I think, just 6 minutes on 4 and 5. You don't need that much time for it. And we'll just keep the same groups. So you guys go. Okay, looks like some people are coming back in. So let's look at the answer key for this. So for number 4, remember H is 1. So I picked like 2 and 3 and 0 and 1 to plug in for X. Get the Y values, plot your points. K is 0, so your horizontal asymptote at Y equals 0. convert class so x equals 1. And then remember, you're going to say all real except 1 for your domain, but all real except 0 for your range. So that's what's happening there. Remember 5, h was 0. So you can just do 1, 2, negative 1, negative 2 for your x values in your table. Get your y values, plot the points. Because k is negative 7, the horizontal asymptote at y equals negative 7. Domain range, all real except 0, or all real except negative 7 for the range. So that's how those graphs look. So any questions about 4 or 5? Okay. So now what we're going to do is quickly just talk about 8.3. I know I'm going to rush it a little bit. I think what I'll do is I'll send you guys a video for 8.3 again to watch over the weekend, in addition to 8.5 and 8.6 videos, and then there'll be a Google form for 8.5 and 8.6. That'll be part of homework. And then, of course, I'm going to suggest some problems to help you prepare for the quiz, which will basically come from these lecture notes. So let me just kind of quickly show you example 1 here, and then we'll wrap it up in a few minutes. So you still, for the more complex rational functions, like we see for example 1 here on page 12, you still want to find vertical asymptotes. And you're still going to do, set the bottom equal to 0. Still going to have that. The horizontal asymptotes are a little bit interesting. This is going to be y equals 3 halves. The reason why is because I did have a discussion with you guys before break, but I know it's been a while. Generally speaking, that's how a rational function looks. This is more of a general rational equation. You have a ratio. We call it rational because you have a ratio of 2 polynomials. And it's 3 situations that could happen. M and N represent the highest exponent for numerator and denominator respectively. If M and N are the same, so each case, your degree is 1, you take the ratio of the leading coefficients as your asymptote. If somehow I had 2x squared on the bottom, so the bottom has a higher degree than the top, then we expect the bottom to increase more quickly when x gets large, so it's y equals 0. And in the case in which the numerator, if I have like say 3x cubed up top, because the numerator is now increasing way more rapidly than the denominator ever would, because the numerator has a higher exponent. So when you get large x values, you're not going to have a horizontal asymptote if m is bigger than n. So in this case, what truly is happening is that m and n are the same. So we just assume that the ratio of the coefficients would be my asymptote. Plus, if I were to plug in like a thousandths for x, I mean, try for yourself if you want. Plug in a big number for x, see what happens. You have 3002 over 1999. That's really, really close to 3 halves. That's really the reason why you have your horizontal asymptote there. X-intercept, you just let y be 0. In order for that to happen, you need the numerator to be 0. So you get negative 2/3. For a y-intercept, you let x be 0. So you have 3 times 0 plus 2 over 2 times 0 minus 1. That's just going to be negative 2 straight up. So now I can actually plot some stuff here. Excuse me. Excuse me. Excuse me. Yeah. to -2 and -2/3. Asymptote 1/2. Asymptote over here. We kind of expect this. And if you were to play in like maybe like 1 and 2, and then you get 5 and 8/3. So that's when we can graph it. I know I kind of rushed out a little bit. I just want to kind of just show you a little bit of 8/3 there. I think what we'll do when we meet again next week, we'll do a little more 8/3 practice in the first maybe 30 minutes of class on next Wednesday before we do the quiz. And then after the quiz, then we'll probably do some 8/5, 8/6 practice. So I'm going to have a video for you guys watching 8/5 and 8/6. I'll post it to Schoology. There'll be a Google form that goes with that. And then I'm going to have you guys just watch 8/3 just so you can review it. And I'll put some, and I'll suggest some practice problems as a separate assignment. Will be just, I'll call it like quiz number 3 prep or something like that. It won't be worth anything, but just be suggested problems to help you prepare for the quiz. Okay, I think that should be it. I don't want to take too much of your guys' time. So, use the time to kind of just relax this morning for your next class. But I'll post some stuff that you guys can do over the weekend or early next week. All right, anything else before we sign off here? No? Cool. All right, so I'll end this meeting so I can record the, so it can process the recording, and then I'll upload the YouTube and I'll share the link with you guys as well.
Okay, thank you.
All right, see you guys.
Thank you.
Yeah.
Thank you.
Thank you.